Hello and welcome back to the episode series of how to build your own autonomous SRE using open source tools and best practices. Before I start, I wanted to introduce myself. Many people have asked me after the last episode, why am I doing this series? What is my background, etc. So I wanted to kind of clear that out and put it off the table. So first of all, my name is Nati Shalom, as you probably know. I'm a serial entrepreneur who's been actively working in DevOps automation space through a previous company that I founded called Cloudify. Previously, I was also founded a company named Gigaspaces, which was more in the big data and memory space, and Cloudify was mostly on the automation space. So if you like, the new world is kind of coming to merge the two kind of concept, both big data and the automation space, all using AI, and that's being coined as the DevOps automation platform. I wanted to do this series to really help people to build their own autonomous SRE and kind of share all the best practices that I've learned through that 20 years experience, but also the things that I'm working on right now, which is actually developing a lot of those autonomous SRE practices myself. And that's kind of the motivation behind this series. So hopefully you're going to find it useful for you to understand both the best practices and the tooling. And I'm going to be able to share with you everything that I'm showing you here. So if you want to get access to that, we'll talk about it at the end. You could get access to it and play with it yourself. So with no further delay, I wanted to switch to the topic of this session. Last time, if you remember, episode 1 was a discussion, an introduction to a framework called K8sGPT, where we played on creating a first autonomous SRE, connecting to Slack, connecting to Gemini as AI endpoints, and detecting out-of-memory loop, which is kind of a common use case in this space. Today, I'm going to talk about, and we ended the session, by the way, on one of the limitations of the framework. One of the limitations is that it doesn't really monitor metrics. It doesn't do it in real time. It usually doing it in batches. So it scans the Kubernetes cluster every 30 seconds, and it calls the Kubernetes API and other analyzers to find an issue, and then it spit out what is called CRDs to define what is wrong, what it finds that is wrong. But if there is a real-time event and we want to be notified about it, it doesn't have access to it, at least not now. So the entire detection pack was to provide more event-driven approach, where I'm introducing a set of services, which I'm going to introduce in a second. And those services is built to integrate with each of the relevant sources, whether it's Alert Manager in the case of Prometheus, but also config map, logging, and each of them will become another source, if you like, event-driven source to the K8sGPT kind of ecosystem or framework. And I'll show you how I'm going to do that. And that will enable us to bridge some of the gaps that we've encountered in the last time, which is slow memory leak. What is included in this pack? This what I call K8sGPT Detection Pack, as the name suggests. I have a service that talks to Prometheus, to the Alert Manager in Prometheus, and monitor metrics. In this case, that will be the primary service that we're going to use to detect the slow memory event that we talked about. We have Event Watcher that talks to the Kubernetes control plane, the same control plane that K8sGPT is talking to, but in an event-driven way. So this will give us more real-time kind of events. A config map watcher, which looking for major configuration changes. So if there's a label that says that this change is touching a critical resource, we want to be notified about it because it may be the actual root cause for failure that we're going to experience later. The audit log consumer is a way for us to actually monitor things that users are doing. So who actually released the new release, who actually did the last operation. So that will give us the, in terms of root cause, the ability to know who is behind a sudden change when we report on a problem. And last it's not really a detection thing. It's mostly integrating into the K8sGPT framework. If you remember last time, we show how we can take all those CRDs and send them through Slack in a nice way. So in this case, I wanted to use the same Slack mechanism and integrate with that. So I'm going to add another Slack service to this pack that will talk to the same Slack that K8sGPT is talking and produce the same kind of format of results. Okay, so with that, I wanted to move to the next part, which is how the architecture is working. So I mentioned earlier that this is an extension to the K8sGPT. This time I wanted to explain what an extension actually means. So the light blue boxes here represents K8sGPT framework. So we have the K8sGPT core, uh, and then we have the result CRDs that it's generating, and the operator that comes with it. And then we have consumers, whether it's the Slack, whether it's Gemini, and the rest of the thing that can consume those CRDs. The K8sGPT Detection Pack is a set of services sitting on that same shared CRDs. So it doesn't overlap in anything. It doesn't really changes the K8sGPT core code. It uses the K8sGPT as another source, and this becomes just another CRD source that will generate more events. From a consumer perspective, it all looks like it comes from one source because it reads the CRDs and just it doesn't really necessarily know what is the actual source behind it. Obviously, we do have labels that will enable you to know the source because it is important information. But from an API perspective and interface perspective, nothing changes from a consumer of this environment. And that's what makes it very nice. Okay, so how does that help us to detect this slow memory? So basically, we augment K8sGPT with the following services: the Prometheus rule evaluators that listens to trends. I'll talk more about it in a second. So it will look for memory growth trends, and it will alert me when that growth trend is going to reach the limits before it actually reached the limits. And then the alert manager, the Prometheus alert manager, would be the one firing that event. And then the service that I've added will listen to those alerts and will turn them into result CRDs in the K8sGPT kind of format. That's kind of the process that we're going to use to solve the specific problem that we discussed in episode 1. One thing about the anomaly detection, and when we're not using, like regular thresholds like 90%, like if you reach 90% memory, we could speed up an alert as well. The problem with that approach is that it's usually too late to detect something like that. When I reach 90%, most likely by the time that I will send the alert, the system will crash, the pod will crash, and it will get into this crash loop. So what I want is to be able to predict that it's going to reach that limit before it reaches that limit. So I would have enough room to actually fix the problem, or at least notify about the problem before it actually crashes the system itself. So we have two layers of anomaly detection here. One of them is at the metric level itself, in which we're doing some statistical kind of baselining. So we look at some baseline. In this case, it's very simplistic. We're looking at the last 6 hours, something like that, as a baseline, and then we're starting to see when things go off base. This is called Z-score, and that's kind of the idea behind it. In general, at this level, we're looking at a single atomic events every time, and we're trying to make the best analysis about the root cause behind this event and the criticality of this event. The thing with autonomous SRE is that the broader picture that you have about the system, the better analysis you could do about the root cause itself. So the point where I'm looking at a single atomic events, I'm always going to be limited by the scope of depth that I'm seeing right now, and therefore I cannot really make a good decision on what is the actual reason for that. It could be a symptom and it could be a root cause. I don't know at this level. And this is why we have layer 2. Layer 2 look at the broader CRDs. So it looks at all the incidents that have been generated by this layer, and it tried to find an anomaly in this layer. So do I see a lot of incidents that are coming from the same namespace or from the same pod? Maybe it means something. So it looks broadly and try to define patterns of anomalies across the board, not a specific signal or source. So that kind of give us already at this level a good picture of how do we trigger events in a relatively reliable way, which already indicates where that source is coming from and not just send an alert. So one of the main problem of those type of system is not to do a lot of false positives. So this is one of the way in which we kill the false positive at the source. before we filter them later in the pipeline. So this diagram shows us the actual demo architecture. What do we see here? So we see three namespaces. The namespace of demo app. This is the same application that we used last time. In this case, we're going to generate the slow memory on the recommended service. We have the namespace of the K8sGPT. This is where our framework is going to live. So previously, it was only this layer, which is the K8sGPT framework. And now I added this set of microservices marked in blue here. So we see Alert Manager Bridge, Event Watcher, Config Map Watcher, each of them connected to a certain source, and then generate CRDs accordingly. The same CRDs that we're going to use here on the K8sGPT. We also added a pack GC, which basically clear the CRDs after a certain time. We don't want to flood the system with a lot of CRDs because this is going to be potentially an event that could generate a storm of events, and we don't want to crash the system because we're generating a lot of events. So the GC here is meant to clean that out. And then we have the regular standard namespace monitoring. That's the Prometheus pack, which comes with Prometheus, kube state metrics, and Grafana, Alert Manager. And we added specifically a set of rules, Alert Manager rules. One of them is related to the memory leak that we discussed here. Okay, so how that's going to happen? Last time when I created the memory leak, it was basically something that I built within the application itself. In this case, I wanted to do it in a more, I would say, formal way, in which we're using a fixture to inject a memory leak outside of the application code base. The way we're doing it is we're injecting a sidecar to the same pod that the recommended service is running. And that sidecar would be the one who is actually flooding the memory. If you remember when we talked about anomaly detection, in this case, we would want to watch for the memory growth trend. And when that would mean that we could trigger the event before it reaches 90%, actually much earlier. So if we see that the trend is approaching to reach the limit, this is where we're going to trigger it. And it could be in 30%, it could be in 40%. It doesn't have to reach the actual limit to trigger the events. That's the main thing here. That goes to the alert manager. The alert manager would route it to the alert manager bridge. The alert manager bridge is a very tiny service that is used for formatting. So the thing is that we have alerts being generated here, but the actual destination could be very different. It could be the actual Grafana, and it could be the Slack, and it could be the results CRDs. Each one of them requires some different formatting of the actual data source that we've created here. In order not to overload the alert manager framework, the alert manager bridge is really meant to do the exact same function, meaning formatting. It's formatting the message to the right destination and connecting it to the destination itself, and we're using it as well to do the formatting to Slack itself. Okay, so another thing that I wanted to touch on what we're not doing deliberately. What we're not doing is deduplication, meaning sending and filtering events that may be repeating, that may be the same, that may be generated on the same kind of error. Why are we not doing it? Because the chances that we will make the wrong decision at this level, because we don't have the full scope of the application, we don't have the full scope of all the errors and issues that have been, incidents that have been generated, we might actually lose events that is important. The only layer that can actually see the broad picture is the layer of application. In the episode 4, I'm going to talk about the Argo CD integration, and this is where we're going to introduce some dedupe functionality to look at how, how we do it at that level. Okay, so with that, I wanted to switch to the actual demo itself. And with no further delay, we'll see exactly how all the things that I mentioned here right now are actually working. Okay, here we are on the same kind of screen that we've seen in the last episode, where we're seeing on the right-hand side the Grafana dashboard of the demo itself, the 4 microservices. We see the CLI that we're going to use to generate the memory leak, and here we're injecting it already. And at the top, the Slack, where we're going to see the actual incident as they've been happening. As we can see, the memory leak has been triggered. And now I added a nice bar at the bottom so we can actually watch the memory grow as it progresses. First, I wanted to check that the K8sGPT doesn't really do anything. It doesn't really detect it because it doesn't watch for monitors. But on the right-hand side, if we look at the LTES metrics, the saturation metrics, we can actually see the memory starting to grow. Also in the bar on the left side, we actually see the memory starting to grow. So we do expect that to be triggered. Next, we're going to inject the actual pack itself. So we're going to call Kubernetes to install all the microservices of the pack, the 4 or 5 microservices I mentioned earlier, and add them to the system. What will happen is that now we're adding a layer that will talk to Prometheus and watch for the memory growth trend, as I mentioned earlier. What I also added is a label that you'll see also at the bottom of that CLI that will give you indication of are we close or are we already in the event itself of seeing that the memory is reached its limit or it's going to reach its limit. So watch for that CLI on the left here for the exact labels that is going to be indicating of that kind of fault. On the right-hand side, we're going to see that the system itself doesn't really detect it, but we can click on and see the actual pack. So I have another pack for the dashboard, another dashboard for the pack itself. And here we can see the specific plugin that I added to watch for the CRDs, something that will show us when alerts are happening. Nothing yet has been triggered, but we can actually see the memory growth being trending. And now we can start to see the label changing. That means that the anomaly detection is starting to see something is going wrong. We still didn't generate any alert or CRD, so therefore the plugin doesn't really show anything here. But soon we're going to see, and here it's getting fired, and soon we're going to see the actual Slack message being triggered. What I added here to the Slack message is also 2 links that will enable me to do the triage. So in this case, when I click on one of the links and I want to see more data about the actual alert, in this case, I need to actually filter the namespace of the demo to actually see the metrics that generated the memory leak. So this gives me the same kind of zoom in into the metric itself and what service actually generated that memory leak. In the same way, I can go broader and see the rest of the metrics in that same context. So that gives me, under that same fault event, what happened in the system, and that enables me. Now we can see also that the plugin showing that the CRD is being generated as we expect, and now we're ready to actually send it to other system in the ecosystem of K8sGPT. We can also see the alert manager is the source that fired this event as expected. So this gives us the view of what is the actual source that detected it. Okay, that's conclude our demo. And that brings me to the last slide in this presentation. What's going to come up next? So next, we've already covered the Kubernetes GPT framework. We talked in this session in episode 2 on the detection tech, but we didn't really had time to actually delve enough on each of the pack and what it actually does, how the alert manager works with rules, all those type of things. So I'm going to add a small episode specifically to deal with that. In episode 3, I'm going to talk about embedded Prometheus. So how do we make the entire pack plus K8sGPT completely standalone agent that you could install on any Kubernetes cluster and wouldn't require any integration with any third party? So we'll see how we do that. And in episode 4, I'm going to talk about safe autonomous remediation using Argo CD. In this case, I'm going to talk about how do we plug in the detection with an action. We also, in episode 5, we're going to talk about some guardrails. How do we control what's going to be executed, how it's going to be executed, where do we put human in the loop for that process, all those type of things that are kind of interesting. Now, I would say that before I end, if you have any things that you wanted to cover, that you wanted me to kind of take a deeper dive or look at to and cover, by any chance, just put in a comment here, and I'll be more than happy to respond to that and tell you and try to cover exactly the topics that you're interested in. The whole episodes and the whole session series was really meant to provide and share with you my experience on how to build your own autonomous SRE. Hopefully that's been helpful for you. Looking forward to see you in the next episode. Thank you.